Hi everyone, I'm Yu. Welcome to our talk on named effects handlers. This work is in collaboration with Ning and Dan, who will show up later in this video. So let me begin with a quick recap of effects handlers. Effects handlers are a generalization of exception handlers where the user can resume the computation surrounding an effect operation. Here's an example written in the Coca programming language. We are defining a new effect, read, that has a single operation, ask. In the handler, we define the interpretation of the ask operation as 1. We do this by passing 1 to the resume function, which represents the continuation surrounding the call to ask. In Coca, we can actually write this program in a more concise way using the read syntax. By writing read handler action, we can evaluate the action under the scope of the handler. As you might have learned from the talks given earlier today, effect handlers can express a wide range of computational effects, and they have industrial applications as well. Compared with other approaches to expressing effects, effect handlers are more composable. In other words, using effect handlers, it is easy to program with different kinds of effects. For instance, if we wish to perform the read and exception effects in a computation, we simply wrap that computation around 2 handlers, one for read and the other for exceptions. However, plain effect handlers are not convenient when we have multiple instances of the same effect. Suppose we have 2 handlers of the read effect and call the ask operation twice. Since operations are by default handled by the innermost handler, both calls to the ask operation are interpreted as 1. But what if we wish the second ask to be handled by the outer handler? One possible workaround is to use masking. For instance, if we mask the effect of the second ask operation, we can skip the inner handler and obtain the expected result. This technique is available in several effect handler languages, such as Frank and Coca. However, programming with masking is cumbersome and non-scalable because it requires us to know what handlers are surrounding each computation. In some sense, it is like programming with the wrong indices, which we certainly don't want to do. What we want is a mechanism that allows us to refer to handlers by name, that is, a named variant of effect handlers. Here, we name the inner handler H1 and the outer handler H2. Then, in the action, we can easily choose the right handler for each call to the ask operation. This is convenient, but unfortunately, named handlers pose a challenge to the soundness of the language. So let's look at this program. We have 2 handlers for the read effect named H1 and H2. Under these handlers, we create an anonymous function that performs the ask operation on H1. At runtime, the inner handler returns this anonymous function, and as a result, the handler name H1 escapes its handler scope. So if we call the return function, we will get stuck because there will be no handler with name H1 surrounding the ask operation. The problem of name escaping has been discussed by 2 recent studies. Their solution is twofold. First, they treat handler names as second-class values. This means handler names cannot be returned from a function or put in a date structure or stored in a mutable state. Second, they mention handler names in the type of expressions. So their type system looks like a dependent or region type system. With these design decisions, they were able to build a sound calculus where handler names can never escape. In this talk, we are going to show you a different approach to the name escaping problem. Specifically, we treat handler names as first-class values and prevent their escaping through the standard rank 2 polymorphism. In the rest of this talk, we first demonstrate two applications of named handlers. We then explain how to statically prevent the escaping of handler names. And lastly, we briefly talk about our Coca implementation of named handlers. Okay, let's start with the applications of named handlers. Our first application is file handling. Here's the signature of the file effect. The effect has one operation called readLine, which receives no argument and returns a string. The interpretation of readLine is defined as the file function. The function takes in a file name fname and an action. Given these arguments, the file function stores the content of the file using a library function provided by Coca. It then creates a handler named f and runs the action by passing f to the action. When the readLine operation is called during the evaluation of the action, it is interpreted as the first line of the file or an empty string. Having implemented a handler, we define a helper function, catlines, that receives a tuple of files and concatenates their first lines. And in the main function, we create two file handlers named f1 and f2 and pass these names to the catlines function. An important observation here is that we are using the name of file handlers as first-class values. More precisely, we put the names f1 and f2 in a tuple and pass this tuple to catlines. This is impossible in the existing calculi of named handlers, where names are second class. All right, now we move on to the second application, which is heap references. Again, we start by declaring a new effect called ref, which has two operations, get and set. For simplicity, we assume reference cells can only hold integer values, but it is easy to implement polymorphic references. After declaring the ref effect, we define the readRef function as the handler of the ref effect. Here we are using Coca's primitive state, which is itself implemented as an effect handler. The definition of readRef is straightforward. We initialize the reference cell to the given initial value and interpret get and set in the standard way. That is, get returns the current value of the reference cell and set updates the value to the given argument. In the main function, we create two ref handlers and use their names R1 and R2 as references. This program works as expected, but the way we create references is a bit different from what we do in a language with native support for references. The reason is that we have to statically instantiate necessary handlers at implementation time. This is not only inconvenient, but also less expressive. Suppose we have a function escape, which creates a reference R and immediately returns it. If we accept this program, we would let the name R escape its handler scope and get a runtime error due to the absence of the matching handlers. So can we realize regular dynamic references using effect handlers? I'll leave this question to Dan.
Thank you, Yu, for the nice introduction. In this section, I will show how we can express dynamic named handlers, where we can, for example, dynamically create an arbitrary amount of references and return them from deep inside the call stack. To understand how this works, we first take a short detour into non-tail resumptive handlers. Such handlers do not only capture the context under the handler, but also change the context right above them. Let's look at a tick example here that leaves a 1+ on the stack when resuming. When we start, the tick handler is on the stack and we perform a tick operation. And this will capture the entire context as a resumption. When we resume, the 1+ though stays on the stack And we just keep evaluating from here on. And when the next tick is performed, the same happens. And again, there will be a 1 plus just above the handler frame. Eventually, when we keep evaluating, we will end up with 3 as the final result. We're going to use the same trick for dynamic named handlers, but instead of the 1 plus frames, we put a named handler there. We use the withref handler again as is, which is just a regular named handler. But also, we use a regular static effect handler, Heap, under which all reference operations are scoped. We call this Heap effect the umbrella effect. In particular, we pass the resume as the action for withref, effectively pushing all named handlers just above the heap handler in the evaluation context. Let's see how that works for the previous escape example. Here is our previous escape example, but now with the heap handler. We start this time with the heap handler already in the context and perform a regular new ref operation to create R1. This yields to the heap handler that captures the entire context again as a resumption, including the umbrella heap handler itself. When withref is executed, the fresh named handler for the reference is installed. And then, when we resume, the ref handler will be right above the umbrella heap effect, just like in our tick example. And the same happens for the second reference, which is also pushed right above the heap handler. And of course, this can create an arbitrary number of references within the scope of the heap handler. These references can now be returned from escape as is, since they're no longer under a direct handler, but instead just returned from the new ref operation. This is a beautiful interaction between named handlers and regular umbrella handlers to kind of allow them to be installed at the scope of the original umbrella handler, no matter how deep you are in the evaluation context. Moreover, it's just effect handler rules without any further special semantic rules for state or something. Since we can now express local polymorphic heaps this way, it is very expressive, and we believe that this technique can be used to express many other kinds of dynamic resources besides heaps. We can even ensure statically that these references now don't escape the heap they belong to, and Ning Ning will show us how.
Thanks, Ilya and Dan, for your great explanations. Now we move to part 2 of this presentation, formalizing named handlers. Having named handlers as first-class value is convenient, but it is also dangerous, as names can escape the scope of their handlers. For example, the program on the right will raise a runtime error as it fails to find the handler h1 during evaluation. The key observation is that h1 is captured by the anonymous function, which is returned from the function f. But when we call this function after we return from f, the handler h1 will no longer be available in the evaluation context. We are going to guarantee well-scopeness of handler names using rank2 polymorphic types, which is a well-understood technique used by, for example, Haskell's runSt monad. Consider the type signature used by runSt in Haskell, which says that for all result type A, if the first argument to runSt is an st monad that is polymorphic over the state S, then the result is of type A. As the argument is polymorphic over the state S, runSt ensures that the state is internal to the computation and it will never escape. With such a type signature, the program below should be rejected, as the state it uses is not internal to the computation. Fortunately, GHC is able to reject this program with a type error. To see how GHC does this and why this program is ill-typed, let's look at the type of read var v. As v is a mutable variable of state S and value bool, read var v is an st monad with state S and value bool. But the argument of run_st requires a polymorphic type, so we would need to generalize the type of read variable. However, since S is captured in the context, it cannot be generalized, and thus the expression fails to type check. Now we have seen how run_st guarantees well-scopeness of states. The question is, can we adopt the same idea of rec2 types to guarantee well-scopeness of handler names? Our answer is yes. In this slide, we redefine the function read, but this time using rec2 types for the action. Like before, the argument action to read takes first a handler name, which is like the st monad to run_st. But unlike before, the handler name is scoped by a phantom type variable s, which corresponds to the type variable s in run_st. And importantly, as in run_st, the whole type for action is polymorphic over s. Now we can effectively prevent escaping of handler names, just like how run_st prevents escaping of states. We formalize the idea of ensuring well-scopeness using rec2 types as scoped effects, which essentially associate effect labels with a handler scope. Note that scoped effects are an orthogonal idea to named handlers, and the scoped effects themselves can be used to encode interesting applications like safe resource interface. Next, we illustrate the idea of using scoped effects to encode a safe resource interface. Consider we want to define a vector effect, which provides two effect operations, push and find. Push adds a new string to the vector and returns its index, while find uses the index to look up the string. We assume the index is an abstract type whose constructor is not exposed. In the handler for vector, we store values of string in the local variable vec, and define push and find using vec. Notice that as we are using scoped effects, the input action has a polymorphic type, which is polymorphic over the scope S. Now it is guaranteed that the lookup in find can never fail at runtime. Namely, the index is always within the bounds of the local list, as each index is uniquely associated with the current handler scope, and we can only use an index returned by push to find elements in the same handler. And whenever we try to use an index we get from one handler to find the index in other handler, we will get a type error, as the scope of the index does not match the scope of the handler. We can rewrite our previous file example using scoped effects, which ensures that files cannot escape its scopes. In Coca, you can define scoped effect using the scoped keyword. In this case, we define the file effect as a named and scoped effect. We can do the same for Heap. But the case for Heap is more complicated, as we would like to prevent escaping of the named effect ref from the scoped effect Heap. To this end, we define Heap as a scoped effect, and at the same time, we define ref as a named effect in Heap. We call that Heap is the umbrella of ref. Note that ref is associated with the scope S from heap S, which are used to associate the references to a particular heap. Now, when we use with ref, the action will take a ref S. All references created by one heap will share the same scope, and so we can, for example, put those references into a list. In summary, in this part, we showed how to guarantee well-scopeness of names using rec2 types as the scoped effects, and we further use scoped effects to guarantee the safety of heaps, which we call umbrella effects. With all these theoretical explanations, you may wonder if everything works well in practice, and Dan is going to tell us more about it.
Thank you, Ningning. The implementation of named handlers using our approach turns out to be actually quite straightforward. We implemented this in the Coca language, which already has rank 2 polymorphic type inference, and can therefore directly express most of the type rules using the right primitives. Furthermore, it turns out that the evidence passing transformation that Coca uses for regular effects can directly be used for named handlers as well, and no new runtime mechanisms are required. Tomorrow we give a talk at ICFP about evidence passing in detail, but here we focus on the essence as it applies to named handlers. Coca uses evidence passing in order to efficiently compile effect handlers to plain regular C code. In particular, with evidence passing, we pass down all the handlers and their stack markers in an evidence vector down to each perform operation. Here we denote it as a W. And then the perform can directly select the handler and marker from the evidence vector without needing to search through the stack. And as it turns out, we can just reuse those marker handler tuples as the name of our named handlers. And we pass those names, those tuples, along explicitly now without ever putting them in the evidence vector. As such, a perform on a named handler now gets its handler and marker explicitly in this tuple and doesn't need to select it from the vector. And now there's, since this is already all implemented, there's almost no change in the runtime mechanisms to support named handlers. There's one other interesting implementation aspect. In the paper, we only describe aesthetically checked named effect handlers using rank 2 polymorphism, but in our implementation, we offer a choice. We can, of course, use the scoped named handlers and get a static check that the name doesn't escape to the phantom type S here. But also, we can just use a plain named handler, and in that case, we get an exception at runtime if it escapes its scope. And the advantage of the latter, of course, is that it leads to simpler types. You no longer need this extra phantom rank 2 S parameter. And since it becomes a runtime exception, it is still sound. Currently, we tend to prefer this in practice, and an exception effect is still fairly benign. For example, even in pure Haskell, any value that's demanded could potentially raise an exception or diverge, and people are generally fine with that. Nevertheless, we're still looking for ways to reduce the annotation burden of the rank 2 types and can kind of use static checking more, and any feedback on that would be most welcome. Thank you so much for listening. We hope it was fun. Please try out Coca at cocalang.org, and you can find the named handler examples under the samples directory there. See also our evidence passing talk tomorrow at ICFP, and come to the Coca and effects tutorial on Thursday. Thank you so much.